Hello and welcome to the 36th lecture. So we're going to continue talking about volumes, and we're going to be doing volumes by slicing still, but now we're going to do more general shapes than simply, or more general solids than simply the solids we get from volumes of revolutions. Volume by slicing. So recall, if A of x is the area of the slice at x, then volume is given by the integral from a to b. And this we discussed. This was the gourmet sausage metaphor. This hopefully seems reasonable to you. This gives the actual volume. Yeah? And then we've done quite a number of examples where we considered the special case of volumes of revolution. So if we have, say, f, this is the simplest manifestation of volumes of revolution. We have some function over some interval, a to b. This is our function f. Okay? We rotate it around, produce our solid object. And then for every x between a and b, we take a slice like this. Yeah? And then the pitch of the slice is this, right? Where f of x is this quantity which forms the radius. So this red line corresponds to this radius, and therefore a of x is equal to pi f of x squared. Okay, so that is the simplest case of a volume of revolution. Now we're going to have to consider cases where we don't have such a simple structure for the slices. We're going to have to think how to slice it, and we're going to have to work out the area of the slices. Again, use the information from the pictures we draw, but now it isn't always going to be just a circle or an annulus, a donut shape. It's going to be more general shapes. So this is the first example. So find the volume of solid whose base is a circle of, I should say really a disk of radius 1 and slices perpendicular base form equilateral triangles. Okay, so this comes with a picture, and I'm not going to do a particularly good job with the picture. So this is our base. I'm trying to do this in 3D. We are, say, slicing like this with respect to x, and as we slice, we have above it an equilateral triangle, so that's really not looking too good. So the slice is perpendicular to the base of this triangle. Think of it as being straight up. Let's try and do a physical model. I don't know how easy this is for you to see, but let's give it a go. So do this at home. Take a blank sheet of paper, draw the circular base. On it, draw an x-axis, something like this, okay? And then draw lines perpendicular to the x-axis, like this. And what we have is that above these lines, we have an equilateral triangle, lifting off like this. Yeah? That's what this object is. So, the nature of the question is that they already give us what our slices should be, because they conveniently tell us that they have to be triangles. So, solution. We are going to draw this thing from the various views that are most helpful. And since we're slicing like this, so imagine the circle here, we're slicing like this, perpendicular to the base. Yeah, we're forming these equilateral triangles. Yeah, I'm going to take the top view of our solid. So take top view of the solid. In the top view, it just looks like a circle, right? And then this is the x-axis. Yeah, and we're doing slices like this. So let's change color for the slice. So here is 0. And then for whatever, let's rub off this x. For whatever x we have, say we have an x here, we're taking a slice down like this. And try and imagine this equilateral triangle lifting off the whiteboard like this. Like this. Okay? All right, so that's the top view. And we see that the way I've set it up, I've made the slices perpendicular to the base and the x-axis, right? So the slices go off like this. They're going to be defined by x. Yeah? As we move x, then we have a different slice. Yeah? Cool. So now, picture of slice at x. Okay, so we're given that it's equilateral triangle. So the internal angles add up to pi, so each individual angle is, or each angle of the corner is pi over 3. Okay, so if we take two knives which are very close together, infinitely close together, and then we slice through this object, we get this triangle, and then we lay it flat, and that's the picture we see. Yeah? And that's true for every slice we take from 0 to x, and it's a symmetrical shape. So we are only going to consider from 0 to x. I'm going to find the volume of that thing, and because the other side is exactly the same, so we just need to double that in order to find the entire volume. Yeah? Okay, cool. So what we need is the area of this slice at x, right? And since we're given the angle, the only thing we need is to actually know one of the side lengths. If we know any of the side lengths, well, they're all the same. If we know a side length, then we're all set. Yeah? So this is the part which is kind of analogous to what we were doing with the volumes of revolution. We have to go from our picture of the slice and identify the thing we're trying to understand onto this picture in order to be able to calculate. The thing we're trying to understand is, of course, the side length. They're all the same, so let's take this side length. So we want to draw with this red pen the line on this thing that corresponds to this red pen here. Yeah? And again, the best way to do this is for you to pause the video and try and do this now by yourself. Try and draw what this line I've just drawn corresponds to on this diagram. Yeah? Pause and try and do that for yourself. Okay, what it corresponds to is exactly this. This solid red line I'm drawing here corresponds to this. Because where did we come from? It came from slicing like this, pulling out the slice and laying it flat. Yeah? So going in reverse, take this guy out, pull it out from this light board. Imagine it's on a piece of plastic. We pull it out, and we slot it back to where it was. So that means we slot this base onto here. Yeah? Some of you are getting this rather fast. Others of you have more difficulty with this. It kind of depends how much playing around with 3D things you've done. If you have a hobby of whatever, sculpting or something like this, then you're in a good shape because you're used to thinking about things in 3D. If not, then it can be a bit harder. But you will pick this up really quickly. So, as I said before, the way to understand this is, if you're having difficulty visualizing this, the way to more quickly develop this mental muscle is to get some modeling clay and start to build these things. So get a lump of modeling clay and try and build something that has this kind of structure, and then take a knife and then slice out a piece of it, and see the shape you get. And you do that, you'll fairly quickly find that your brain starts to see these things and be able to just move them around in your head without physically making a model. It's the equivalent of drawing the pictures that I'm always talking about, except now it's in 3D, and that is our job as a mathematician. So as to this is not cheating in any way. This is how we do it. This is how we understand things. So if this isn't clear to you, do this. Get some whatever substance you can mold into some sort of shape. Some bread dough or anything, and just mold things into shape and cut things out of them, and you will quickly find your brain takes over and sees what kind of things are happening. Okay, cool. So this thing slots into here, so this length corresponds to this length. And now we're in good shape because this is something we can figure out, because this is a circle of radius 1, right? And the quantity we're interested in is the length of this red line, which is twice the length of this quantity. And this quantity changes with respect to x, right? When x is close to 1, it goes towards 0, and when x is 0, it's 1, right? So this quantity is actually a function of x. So let's think about this a bit more. So if we give this point coordinates x, y, then this point xy lives on this circle. It lives on this circle. So it satisfies x squared plus y squared is equal to 1. In class today, some people were doing this. They were going, okay, well, what I see here is a triangle like this, and the hypotenuse has got length 1. So therefore I can work out the opposite side, because this thing has got length x. And that's entirely valid. I was very pleased with that. But that's exactly the same thing as the fact that x and y live on the circle, right? The reason this is the equation of the circle is because of Pythagoras. So that's just doing things a little bit more by hand, but that's totally valid. Totally happy with that. So if we think about it this way, then this side here is x, this side here is y, the hypotenuse is 1, and therefore x squared plus y squared equals 1, and we're the same thing. And what we really want is what y is, because y is this length here. Y is this length here. So we can solve for y. So then y is equal to the square root of 1 minus x squared. So then we have what y is in terms of x, which gives us that this thing is 2 square root of 1 minus x squared. Super. And now we're really in strong position, because we have one of the sides and we have the angle, right? And we know that if we have a triangle, then the area is just the base times the height divided by 2. And we've discussed this before, because if we have a triangle, any triangle at all, if we just complete it to form a rectangle, then the pieces that we add have got the same area as the triangle itself. And then if this is the base and this is the height, then the area of the rectangle is just base times height, but the triangle is going to be half of that, so as we see. So that's the formula for the area of a triangle. So we just need to know this dotted line here, and we're all set. But then this is trigonometry. So let's just draw the one side. So we have this thing is pi over 3. We have half of this length here, so this thing is square root of 1 minus x squared. And then we need to know the opposite side. So we know that, let's call this side b, and we know that tan of pi over 3 is going to equal to b over the square root of 1 minus x squared. Okay, cool. So maybe you already know what tan of pi over 3 is, right? So you're expected to know these basic angles tan, cosine, sine. Yeah? But as I've said many times, I'm opposed to memorization. Memorization is what we want to avoid. We want to be able to work things out from pictures, and we can. And this is how we're going to do this. So if you are happy with tan, if you already know this and you don't want to have another reason for knowing this, then don't be concerned with what I'm about to explain. But for those of you who would rather be able to work it out than memorize it, then let's do the following. So let's put this in a box to figure out tan of pi over 3. Then we draw a picture. So this is our angle, pi over 3. Yeah? And we know that this is half of an equilateral triangle, right? So the other side would look like this. And all these side lengths are the same. So let's make things really convenient for ourselves, and let's make all the side lengths 2. So this is 2, this is 2, and this whole thing here is 2. But that means that this side length here is 1. Yeah? And then by Pythagoras, we know what this side is, because this side, let's call it c squared plus 1 squared is equal to 4, which implies that c is equal to 3. Square root of 3. Like this. Yeah? So then this thing, let's get rid of this, is the square root of 3. Cool. And then we can read off what sine, cosine, tan of pi over 3 is from this, because we have all the sides. We have all the sides. So in particular, what we wanted to find was tan of pi over 3, and it is just the opposite divided by the adjacent, which is square root of 3. Now, I just chose 2 because it's convenient, because I end up with 1 here. I could have chosen any number. I could have made an equilateral triangle with each side is 5, or each side is 12, or anything. I'm going to come up with exactly the same result, because I'm still going to be dividing this by this, and it's still going to be square root of 3. No? But this, to me, is clearer or easier than trying to memorize this, because you can just see it, right? You just set up the equilateral triangle, and that has to be the dimensions of this length and of this length, and therefore this has to be this, and it's just there. Yeah. And not only does this give you tan, it gives you all the other trig functions you want as well. So I recommend doing this kind of thing rather than memorizing angles. You have to do this, and then you'll have all of the trig functions rather than memorizing 3 separate trig functions. In other words, memorizing cosine of pi over 3, sine of pi over 3, tan of pi over 3. This picture contains all of that. All right, cool. So back to our task. Since we know this thing is just square root of 3, then we know what b is. So therefore, is equal to square root of 3 times 1 minus x squared. Yeah? And this is the b. This is the b that we just worked out. So therefore, area of slice is the height times the base over 2. So it's square root of 3, 1 minus x squared, the base, times, that's the height times the base, this, divided by 2. And this turns out to be just square root of 3, 1 minus x squared. Cool. So now we have the area of this slice at x, and this is our a of x. And then our task is just to integrate it. Yeah? So let's create some space and integrate this guy. Okay, cool. this is our guy, right? We are going to integrate from every x between 0 and 1. Yeah? And then we're going to multiply by 2 in order to get the other side. So the volume is equal to twice the integral between 0 and 1, the area of the slice, which is this thing we just worked out, square root of 3, 1 minus x squared, oops, dx. And now we're really in good shape because this is just a totally standard integral, right? So we have 2 root 3. And we want to find the antiderivative of this thing, so it's going to be x minus x to the 3 over 3. Yeah, we put in 1 into this, we're going to have 1 minus a third, which is 2 over 3. We'll put 0, we get nothing. So then we're just going to have 4 of root 3 over 3, which is just 4 over square root of 3. And that's the answer. Cool. All right, let's go over the steps that we did. What did we do? Okay, so we have our 3D type picture. We actually drew something on a piece of paper and visualized these equilateral triangles coming up. Yeah? And then we decided which way we're going to slice it. In this case, it's easy because they're giving us the way to slice it is actually defined out of slices. Yeah? So we're going to slice it like this, where we get the equilateral triangles. Yeah? Cool. And then what is apparent to us is that we're going to need to know the dimensions of these slices. Yeah? You know, dimensions, in particular of the side lengths, because that's all that defines the equilateral triangle. So we drew a picture of the thing from above. Yeah? Because we drew a picture from the thing from above and we visualize slicing it, yeah? Then this thing here, from here to here, corresponds exactly to the base of the triangle that we sliced out of it. Yeah? So to find out the side length of the triangle, we just need to work out this length. Yeah? And then we go, okay, well this looks promising because what I see here is a circle. Yeah? So if I take this corner point right here of this internal triangle, I take this point right here, then what do I see? Well, it has to satisfy the equation of a circle. Yeah? X is the variable we're using to slice, right? So we're taking every x between 0 and 1, and what we want is this quantity in terms of x so that we can integrate it with respect to x. Yeah? So we need the y in terms of x, and again, because this is on the circle, yeah? We can write y in terms of x. It's given by this. We just solve for it. And that's this quantity here. Yeah? So the actual base is twice this length, which is right here. Cool. And then it is just a bit of trigonometry. We need to know the height. We can find the height. We need to know what tan of pi over 3 is. You can either work it out or you know it. There you get the height. This is the height. Therefore, the area of the slice is the base times the height divided by 2. It's just this. We integrate it. It's just a standard integral. So the hard thing is to decide what pictures you want to draw so that you can identify the relevant things you need in order to calculate the area of the slice. And what should have come to you, or what should come to you with enough practice, is that the right picture to draw is the top view of this particular shape. Huh? Cool. All right, so it's a bit harder than surfaces of revolution, but we can do it. Huh? We can do this. All right, I'm going to raise the board, and we'll do another one. Okay, next question. So, example. A wedge is cut out of a cylinder of base radius 4 centered on 0 by 2 planes. One is perpendicular to the axis of the cylinder. The other intersects it with an angle of 30 degrees. And the intersection includes 0. Find the volume. Okay. Start by trying to draw a 3D picture. Like this. Let's go down like this, and let's make that bigger. Like this. Like this. We got some radius. Well, we got the radius is equal to 4. I regret putting the radius on that side. Let me put it somewhere else. Let's just remember that radius is 4. Put that in later. So we're slicing it with 2 planes. The first plane is just the plane perpendicular to the axis of the cylinder. So that's just the base. And the next plane comes in and intersects it at 30 degrees like this. And the intersection includes 0. So the line of intersection is this thing like this. Okay, so this is like a kind of a chunk of cheese. So imagine this cylinder again, take your piece of paper, draw a circular shape. Draw a circular shape on a piece of paper. So the axis of the cylinder comes up like this. One of the planes is the base, the other plane comes in and intersects it at 30 degrees. So this is the thing. So imagine this thing slicing out a chunk of the cylinder. That's what we have here. So it kind of looks like a wedge of cheese. Yeah? Cool. All right. So our job is to find the radius of this. And now let me put the, sorry, is to find the volume of this. Now let me put the radius in here. So the radius is 4. And now we're not told how to slice, so we have to think about it. We have to think about how to slice. Yeah? So when we did this in class, there were a number of suggestions. So let's imagine that my cylinder is here on the table. My chunk of cheese is like this. Yeah? Chunk of cheese is like this. How should we slice it? Well, we have lots of options, right? If we slice it like this, what do we get? We get these kind of parts of a circle, right? Semicircular things. They're not actually semicircles because it's not half a circle, but it's going to be a straight edge and then part of a circle if we slice like this. That's not the nicest shape, right? It's not the best thing to deal with. Yeah? So let's not do that one. Yeah? What else could we do? We could slice like this. Could slice like this. Yeah? Yeah? Oh, sorry, we just did that one. Okay, we did this slice. Yeah? We get this semicircular thing. Yeah? What else could we do? We could slice like this. We could slice straight down. We could slice straight down. Yeah? Just like this. Then what do we get if we slice straight down? We get these kind of rectangular shapes, right? Yeah? Which is okay, but let's see if we get something simpler. If we slice like this, then we get triangles. Then we get triangles. And the triangles we get have this angle here at the corner 30 degrees every time. Yeah? So we only need to know one of the sides of the triangle to figure out everything else about it. Yeah. So this thing seems like the best choice. Yeah. This thing seems like the best choice. This is the worst choice. Yeah. This is the worst choice. And this might be okay. And we could try this if the triangles don't work. Okay, so what pictures do we need to draw? Well, we're going to have the picture of the slice. So and we agree if we slice like this, we're going to get a triangle with 30 degrees right here. And then we have to think what view of this thing is helpful for us to actually find the dimensions of this. Yeah? And what should come to you after a little bit is that the top view of the solid is the best thing, because if we take the top view, then we see a kind of circular shape like this. This stuff on this side is the stuff we're interested in, so we can actually get rid of this. So the top view of our solid looks like this, yeah? And we are choosing to slice it like this. Choosing to slice it like this, yeah? And since this is the way I drew it, I mean, I could have drawn it the other way around, where the flat part is like this along the x-axis, but I did it like this. So if we do it like this, then if we're slicing like this with these horizontal slices, then they're defined by some y, right? So every y between 0 and 4 defines our slice, yeah? Again, this is the top view. Cool. So this is the pitch of the slice at y. So we're going to be integrating with respect to y, and we want to find the dimensions in terms of y. Yeah? That's our task. Okay, now, again, the game is to draw the line on here that represents something here, anything actually. Any of these sides will be good, right? Because we have one side we can find anything, yeah? And the side we're going to choose is this side. So the best thing is for you to pause the video and then try and draw on this picture the side here that I've highlighted in red. Yeah? Try and identify on this picture what this line is on this picture. Huh? Pause the video, give that a go. Okay. What you should have come up with was that this corresponds to this. This corresponds to this. Yeah? This corresponds to this. And it's the same reasoning as before. So we got this by slicing down like this and taking out our piece and then laying it flat here. Yeah? And in reverse, we take this piece, lift it off, slot it back in. Yeah? Then this red line corresponds to this red line here. Yeah? Cool. So we need to find the length of this red line in order to find the length of the base of the triangle, and then we're in good shape. Yeah? And we need to express it in terms of y. So this point right here is, say, xy, right? And this is the x-axis. Let me change color. This is the x-axis, yeah? So right here is x, yeah? And therefore the coordinates are xy, yeah? And we know it lives on a circle again. So we still have x squared plus y squared, but the circle's radius 4, so now this is 16. Yeah? Cool. So again, our task is to find this length, but this length is just the same as the x-coordinate, as we can just see. Yeah? So x is equal to the square root of 16 minus y squared. Cool. So then this length is exactly this thing, so we can fill out this. This is the square root of 16 minus y squared. Excellent. All right, and now we're in good shape, right? Because then it's trigonometry. So we want to find this length here. Yeah. And by trigonometry, we have that b over square root of 16 minus y squared equals tan of 30. I do not have a picture to give you tan of 30, and it's not a simple one. So this thing, I'm hoping if you had this in an exam, it wouldn't be one of the standard angles you meant to know, and you'd just be giving it, and it turns out to be 1 over root 3. Huh? So then that means that b is equal to, it's not 1 over root 3. No, it is 1 over root 3. I'm sorry. It's 1 over root 3. So that means b is equal to square root of 16 minus y squared over square root of 3. And then the area of the slice. So is the base times the height divided by 2. So this is the base. The height is this thing. So we're going to have square root of 16 minus y squared times square root of 16 minus y squared over 2 root 3. So that's going to be 16 minus y squared over 2 root 3. And now we're all set because we're going to integrate every slice like this from 0 up to 4 because this thing has got radius 4. Yeah? And then we're going to multiply by 2 because we want to get the other side too. So volume is 2 times this stuff. Integral from 0 to 4 of this stuff. 16 minus y squared over 2 square root of 3. Obviously the 2's cancel, so we have 1 over root 3. And then just this integral, and this is a standard integral. So here we're on the home straight because we can just integrate a polynomial. We can certainly do that, right? 16, the antiderivative will be 16y, y to the 3 over 3. And we notice some stuff here. So when we put y 0, nothing comes out. If we put y is 4, then we have 16 times 4, which is going to be 64. But it's also the same as y to the 3, because y to the 3 is 4 times 4 times 4, so it's 4 times 16, which is again 64. So we can factor out 64 from all of this. And then what we have is 1 minus 1 over 3. And then that's just going to be 2/3 here. So we're going to have 1, 2, 8 over 3 root 3. And let's see if that's right. Indeed it is. Cool. All right, so let's go through the steps. We drew a 3D picture. We tried to visualize it on the table here. Yeah. This time it was harder because we had to decide how to slice it. So we considered the options. Yeah? And of all the options, the simplest shape was when we sliced it down like this. Imagine it on this table. We sliced it down like this with lines which are perpendicular to the intersection between the two planes, because that gave us triangles with this angle of 30 degrees. Cool. So since we're slicing like this, we made a top view, and then we see that the way we've drawn this picture, we're slicing with respect to y. Yeah? So y is our variable. Yeah? So we're slicing at y, and then we need to find the dimensions of this guy in terms of y. Yeah? And then we identify that the base of this thing is the same as this. Yeah? Yeah, we just visualize that because we slice this, we lay it flat, pull it out, slot it back. The base here is this. Yeah? Cool. Then we look at this picture. We see that, okay, we're in good shape because there's a lot of structure here. This is part of a circle of radius 4. So this thing here, this point here with coordinates x, y satisfies this equation, and the x is exactly the length of this line. Huh? cool. So we find the length of the base. Trigonometry gives us this length, which is this. Therefore, the area is this times this divided by 2. It's that thing. We integrate it, we're fine. The hard part was drawing these pictures such that we can find out the dimensions of the slice from the pictures we're drawing. That's the new skill you have to learn. Okay, cool. Let's do one more example. Okay, final example. Find the volume of a pyramid. I have no idea how to spell pyramid. Whatever. How do you spell this word? I'm sure it's not like that. Okay, it's embarrassing. Embarrassing attempt to spell pyramid. All right, whatever it is. You know what I'm trying to say. A pyramid whose base is a square of side length and whose height is h. Okay, so solution. All right, this is a bit easier to draw, so it's kind of looking like this. Yeah, and the side length here is L, and the height, I have to represent it here, but the height is H. Okay, again, take your piece of paper, put it on the table, draw a square base. And then visualize the pyramid coming out like this of height h. So L and h are just these fixed quantities. We don't know what they are. We're going to have to define things in terms of L and h. Okay, but they're not the variables. They're just fixed. Okay? So with this, we have to think how to slice it. Yeah? So we have some options. We could slice it straight down. But if we slice it straight down, we're going to get these four-sided kind of shapes right here. They're not going to be rectangles, but they're going to have four sides. It's not going to be that easy. Yeah? We could slice it like this. If we slice it like this, then we're going to get squares. Right? We're going to get squares. And that is a very simple shape because we just need to know one of the side lengths to find the area. So that would seem to be the best way to slice it. In class, someone suggested slicing it down the diagonal, which would give you triangles. Agreed. Yeah? But that's probably going to be harder than just dealing with squares. So we're going to go for squares. Huh? So, picture of the slice. Will be a square. Okay, and then we're going to think of what view of this thing we want in order to get this thing as a slice. Huh? And what should come to you after a bit of thought is that the best thing is the side view. So, side view. If you draw the side view, then it looks like this. Right? Height is h, and then this base here, this will be L over 2. Well, the entire base is L, right? This is L. So from here to here will be L over 2. Cool. And if we're going to slice it like this, then every slice comes like this, and it's going to be defined by the y. Yeah? It's going to be defined by the y. Now, here's a point. If we use y, yeah? Slice like this, and then define it in terms of y. Then this thing here will be a function of y. Right? This length here will be a function of y. Let's write that better. Yeah? And then what will that be like? Well, that will be a function where as y gets towards h, it goes down to 0, and as y goes towards 0, it gets towards L over 2. And that's okay, but since we can choose whatever way we want to slice it, we don't have to count this thing as our variable. We could count this thing, the distance from the top, as our variable. And that seems to me a bit nicer because the distance from the top is such that as this distance grows, then this thing grows. And that's easier to visualize, easier to handle. It's not a big deal. We can certainly do it with this y, but it makes things a bit simpler. And we have the right to start slicing from the top. It makes no difference. You know? If you think about the metaphor of the sausage, the fact that we slice from left to right as opposed from right to left, it's completely irrelevant for how this works. Yeah? So we can indeed start from here and then slice downwards. And let's do that. So instead of using y like this, get rid of this y. I'm going to slice downwards, and I'm going to call it something else. I'm going to call this thing from the top w. So w is the height from the top, or the length from the top of, how do I express that? W is how far down from the top we choose to take the slice. Yeah? And then we're going to try and find the length of this slice in terms of W. So this is this thing. I'm going to try and express this as f of W. Okay, cool. And I'm happy with that because, again, as W grows, f grows. Yeah? And with that, we see that this stuff here exactly corresponds to this right here. Yeah, exactly the same reasoning. We slice through this to get this shape here. So if we take this up, put it back, slide it back in, then this yellow line is this line here. Yeah? Cool. All right, so it's good enough for us to find f of w because this thing is twice f of w. Cool. All right, so f of w is some function of w. And if you look at this for a little bit, what hopefully should start to be apparent to you is that it's a very nice function of w. Yeah? So if we just lay this out flat, put it over here, then if this here is 0 and this here is w, then this is like f of w, right? And what we know is that when we get all the way down to h, so this is h here, then this distance right here is L over 2. Yeah? And what we want is the formula for w. Yeah, and as you can see, this is actually a really nice function. It's a linear function, and it's a linear function that goes through 0. Yeah? So what we need is to find explicitly the linear function that goes through 0, which has the property that when we are at h, the height is L over 2. Yeah? And a moment's thinking should make it clear to you that that isn't a hard thing to do, because a linear function is just defined by its intercept and its slope. Its intercept is 0. We set it up that way. Yeah? And its slope is how far up or down it goes divided by how far along. How far up does it go? It goes by L over 2. Yeah? How far along by h. So the slope is L over 2 divided by h. Yeah? Yeah? So this linear function, f of w, is just going to be L over 2h times w. That thing will do it, right? Because it's just defined by the slope. And you can just check for yourself that f of h is going to give you L over 2, which is what we want. So it's going to the right point. It's definitely the right function. Yeah? So we explicitly have what this thing is. Yeah? So then we explicitly know what this side length is. Yeah? So this side length, therefore, is twice f of w. So it's just L over h times w. That's this side length. Yeah? Cool. So the area of the slice area of slice is this thing squared, right? It's L over h times w squared. Yeah? Cool. So we just have to integrate this. Yeah? So we are starting from 0 and we're going all the way down to h. So we integrate from 0 to h. Yeah? Just this thing. So it's going to be L squared over h squared w squared. Yeah? dw. Now, L and h are just fixed things. They're constants. They're given in the question. L could be 15, h could be 12, whatever. They're just fixed things. They are not part of this, right? So we can just pull them out. They're just constants. And then this is just an easy integral, right? Okay, so only do this. And then we put in this h, we have and then what is this? This is L squared h over 3. And that is the answer. Yeah. Cool. Let's go over the step. What do we do? We had this three-dimensional picture. We decided how to slice it. We're going to slice it like this. It's going to give us squares. We need to figure out the side length of the squares. Best way to do this is to look at this sideways on. Yeah? We look at it sideways on, then this yellow line corresponds to this side of the square. Yeah? And then what we see here is that we need to describe this length in terms of the variable we use to define which particular slice we take. We thought about doing it from y, from the base, but after looking at it a bit longer, it's more convenient to define the slice by the distance from the top with w. Yeah? So then we want f of w. Yeah? If we can find f of w, then 2f of w is this thing, and then we're all set. Yeah? So we look at this, try and understand, we want to understand what f of w looks like, what we know about it. We know when w is 0, it's 0. We know that when w is equal to h, f of h is L over 2. We know it's increasing and it kind of looks like a linear function. Yeah? So we put that over here. Yeah? And indeed, this is what it looks like. It looks like a linear function. Yeah? And then we can find what this linear function is explicitly, because all we need is the slope of the linear function. Yeah? The slope is how far up or down divided by how far along. Yeah? So the slope is L over 2 divided by h. Yeah? And that gives us explicitly the linear function. Yeah? And therefore, we have twice this is the side length now given to us, explicitly gives us the area, and then we're home set, right? So again, the main thing is to figure out how you're going to slice it, and then draw the pictures you need to be able to find the dimensions of the slices. All right, so this is a harder topic for many of you. But I like this topic for lots of reasons. You have to start to visualize things in 3D, which is a very valuable thing, particularly as you study multivariable calculus, as I hope very much you all do. This is a skill you need to develop. Yeah? And by doing this stuff of constantly going backwards and forwards from the pictures to the calculations, you can break this difficult looking problem up and understand it. And again, this is an extremely useful skill. More useful than actually carrying out this integral is being able to break down the information in pictures where you can figure out what you have to do from the pictures. So I like these kind of problems, and it's also extremely good guess that this will be one of the free response questions, either for this midterm or for the final, because there's multiple stages to this. It's not something we can easily test with multiple choice. So being able to do this is worth probably 15 points as opposed to being tested on multiple choice, which is worth 5, right? So this is like 3 times the amount of points. So it's well worth getting good at this. Huh? So please practice this. Please watch these videos. You might have to watch this more than once. Don't be intimidated by this. This is not a difficult thing. It's just a new thing for many of you. If you do this, if you persevere through this for a couple of difficult examples where you struggle and you have to think hard, you'll start to pick it up really quickly. Yeah? So just persevere through the first few examples where you're stuck, where you have to try a number of things to get it to work. Don't give up. And then this will come to you. And you'll be able to do all these questions. You'll feel very confident with them. All right, cool. So that's it for today. Have a great day.